My name is Emily, and I'm super excited to be moderating our chat around sustainable computing, systems, and AI. We have an incredible lineup of speakers with us here today, leading some groundbreaking work in the space. So we have Minlan Yu, Lisa Mini, and Kathy Wu. So feel free to sit back, listen in, and jot down any questions you have for the Q&A section we have at the end. So let's get started. To kick things off, I would love for each of you to introduce yourself and share a bit about how your work is driving sustainability in the space of computing and AI.
Okay, thank you for the introduction, and nice to see all of you. My name is Minlan Yu. I'm a professor at Harvard. My work is mostly working on data center infrastructure, so I work over the years on making it more efficient, more performant, more reliable, and also more recently more sustainable. So on sustainability part, I'm part of the big effort from NSF expedition on Carbon Connect, essentially how to making computing infrastructure more sustainable and more carbon efficient. And to our surprise, like computing infrastructure actually takes 2 to 4% of the worldwide carbon emission. If you count energy, it's been growing like 10 times every decade. And more recently, with the drive of machine learning models, support of machine learning applications, energy usage have grown exponentially. So we work on how to make these data center systems more sustainable. And should I continue with 5 minutes? Or? Okay. Okay, great. So we're also interested in how power grid and data center integrate. So we actually are going to launch a new power and AI initiative at Harvard, trying to bring grid operators and data center operators together so that we can jointly solve this big energy issue. Specifically, my work focuses on how to build software systems that can provide better sustainability for data centers. And the typical approach I take is how to jointly optimize the energy and the systems and how to jointly optimize the carbon usage in the operation, but also the carbon usage during manufacture. So if you look at data center, they have both the data center GPU devices or the servers that takes energy while you're operating them, but they also take energy while you are manufacturing them. So how can we minimize the overall carbon emission for the whole data center operation in the end-to-end life is the main question. So the way to reduce the carbon emission is to make sure we can reuse the hardwares, recycle them, even though not all components is working. So from software system perspective, it's how do we build systems that can leverage these heterogeneous devices, old versions of GPUs, new version of GPUs, heterogeneous memory, compute, and network resources so that we can build efficient systems on top of all these diverse types of devices. So in particular, I can give a few examples on how my research works. We have been building software systems that can run on these heterogeneous hardware settings. So we have been building new scheduling solutions that can make the inference jobs that can map to different different heterogeneous devices. So for example, how do we use different versions of GPU? So some runs more high efficient models with high accuracy, some runs on smaller models but more energy efficient. How do we distribute requests among these different types of GPUs so that it can bring you more efficient performance and high utilization? But in addition to that, in addition to GPU, you would also have CPUs. How do you have kind of asynchronized pipelines that can be mapped to these different type of computing devices so that we can get even further energy efficiency? And finally, there are also a lot of other accelerators like network interface card, programmable switches. These are devices that are less capable than the computing devices, but they are good at processing a lot of packets. They can do compression, encryption, and also aggregation and fast speed. So again, how do we identify the right functions to run on these devices? So together, we can build an end-to-end system that can build higher efficiency. And then in addition to making the system works for heterogeneous devices, another group of effort we're working on is making systems more elastic. So the way to think about it is as you run large-scale systems and you want to consume a lot of energy, you cannot accept that the energy gonna be sustainably afford the system to be running smoothly. There will be failure happens all the time. If you're using renewable energy, the supply of the energy could vary over time. So how do you build systems that can elastically adapt to the energy changes, to the fluctuations of resources? So how we will also work on how to schedule jobs, how to remap jobs in terms of their parallelism schemes, their model choices, so that we can build elastic computing systems on these kind of variable resources. So we have built systems that can also quickly react to these kind of energy surge events by migrating jobs to other places. Of course, you want to minimize interruption to all of these jobs. And finally, the third piece my group has been working on is how to build better accounting systems. So the first way to solve sustainable computing problem is to build measurement systems and also benchmarking systems that can understand the energy usage of different systems from hardware to software. So we have been building telemetry tools that can carefully account all the different types of, especially machine learning systems that's running in data centers. So we can be best informed on where the energy is used, where is the most waste of energy that we can save on. And the hope is that once we build a benchmarking system, we can use that for helping data center operators to know how to make their system more efficient. We can help manufacturers to answer even what-if questions, like what if I build a more energy efficient devices? What if I have different kind of ASIC chips to support my design? What's the impact on the overall data center machine learning application in terms of their sustainability? And finally, we feel this accounting could also help the grid, power grid, to help them to decide where to transmit the energy to if they have limited energy, and how to schedule the storage and the transmission of energy so that they can maximize the use with current grid capacity, and also to forecast on future placement for investment. So overall, I hope our work could, we can all work together to improve the sustainability for data centers, and the effort really need to bring all parties together. As I mentioned, carbon emission not only happens at operation times in data center, but also manufacturing times. So it's important for device manufacturers and data center operators to work together. It's important for data centers and the grid power operators to work together to jointly solve the energy burst issue. And it's important for academia and industry to work together so that we can build a better benchmarking system, better optimization systems for these data centers. And finally, we hope our work could inform government to design the right policies towards better sustainable data centers. And that's a rough overview of what my work is, and look forward to more discussion.
Hi, I'm Lisa Amini. I'm the site lead executive for IBM Research Cambridge, which is just a couple of blocks down the road. I also lead our data and AI research platforms mission globally. So that mission is about basically, if you think of IBM, probably you're aware that IBM has a long history with databases, DB2, and so on. So IBM actually has a lot of products in databases, data lakehouses, data warehouses, knowledge catalogs, ETL systems. All of these systems are all about just managing the data estate for an enterprise. What we've been focused on most recently is how do we leverage generative AI to try to improve those systems and to also improve those systems so that they can better support generative AI workloads. Okay, so when we talk about improving the systems, the idea is that these data management systems, as well as the people, the resources, the human resources that it takes to manage them, consume a lot of energy, right? So what happens is that many different problems arise. So for example, you get new data in. Often that data has to be labeled. Once it's labeled, then it has to be further curated. It has to be harmonized with existing data. It needs to be, resolved and mapped against existing entities and so on. So we can use Gen AI and large language models to try to take on some of that responsibility. And that reduces the human workload. But what it doesn't do is it doesn't necessarily reduce the energy workload, right? Because these models obviously are taking a lot of resources in order to run. However, one of the big ways that we do that is that we're looking at trying to sort of right-size the model to the task, right? So we don't just leverage the very large models, which are generally could be in the hundreds of billions of parameters. But we also work with smaller models. So we try to pick models that are more like in the tens or 10 below billion parameter models. We find that putting those together in a system or in a workflow, we can often do better than what we would get with a single very large model, because it can be more directed to what the task that we actually need. So we work a lot in trying to combine these two and make sure we're doing it in an efficient way. The other thing that we do is to try to make the data management systems better for Gen AI workflows. So that's not just about making the data more accessible, more discoverable, more able to be searched and retrieved and all of these sorts of things. But when you think of it at the intersection of power, one of the things that we've observed is that, and other people have reported on this as well, that oftentimes, surprisingly, in the news, we always hear about, how much energy GPUs are consuming, because, people are deploying these very large, dense farms of GPUs. But what others have also shown is that, hey, look, but if I take workloads and I accelerate them on GPUs, I often can consume less power, less energy, even less water than if I were running it on CPUs. So as another example of something that is an interesting idea, I believe, in this area is databases, data lakehouses, warehouses, all these sorts of things. They all run on CPUs. They always have for a very long time. However, what's also happening in various different ways is to sort of reinvent databases such that they run on GPUs, right? So it can either be by taking the existing operations and the existing structures, running and just accelerating those operations on GPUs, or it can also be in terms of saying, hey, maybe I should actually just rethink the entire database. Instead of having the operations that we have today, could I do these as tensors instead of the data structures that we have today? And what's nice about that is that it also sort of changes the game, because one of the big problems we've had, and part of the reason why there's energy efficiency issues with these databases, because we kind of keep reinventing and maybe not taking advantage of our prior investments. So we have the databases, and then we said, well, those are great for transactional, but maybe not so great for some of my analytic workloads. Could I have a data warehouse? Okay, well, that's pretty good, but it's still consuming a lot of power because of the way that they're managed and so on. So can I have a lake house, which is kind of a lighter touch? Okay, well, that's pretty good. But now that I need to search on, more semantic kinds of operations, more natural language, how about if I do that with vector databases? Okay, that's good. But wait a minute, when I organize it that way, wouldn't it be better to organize this as, instead of on the row basis, on a column basis? So they have these columnar databases. So we keep, in the data management space, we kind of keep reinventing to try to go after a targeted thing. And then you're spinning up all that data. You keep taking the data, and then you say, okay, well, let me re-represent it as vectors, or let me re-represent it in the lakehouse, so we'll confine it. So one of the things that we're looking at as well is to say, maybe we should take a step back from that and think about a more unifying representation for data management, and likely within that vector and tensor space, and reinvent all of those types of operations so we can have more of a holistic approach, and hopefully also be able to take advantage of that accelerated hardware. So it's a variety of different types of projects, all towards that problem of data management. And what I would say is that sustainability has kind of been a long problem with respect to databases, data management. I think some of the things that you were talking about as well, this idea of how do we locate the data closer to renewable sources? How do we have systems that monitor the consumption, the power consumption, the storage footprint that we're using, and so on, and try to continuously optimize that? So that's another factor within all of this. So that's the area pretty much that I work within, and it's, like I said, it's always been something that's been had a need for efficiency because of just the huge scale for it. But now, what I would also say is that previously a lot of this was structured. The data that people really, really, really cared about in enterprises was the structured database. What was structured data? What was in databases? But now with all of the unstructured, natural language, images. That's really just changing the numbers dramatically. So it's putting new pressures on all of these types of systems. So that's the space that I work in.
Thank you. Hi, everyone. My name is Kathy Wu, and I'm an associate professor at MIT. And I first just want to say how excited I am to be here. It's been so long since I've seen this many women who are technical in one room. It must be like, several years before the pandemic. So I'm just so excited about this. So I'm going to give a bit of a different perspective. So what we've heard about so far is, to some extent, sustainability for computing. And this sort of came up in our pre-discussion, but there's a different perspective, which is computing for sustainability. And so I'll be sharing probably throughout the panel a bit more from the application perspective. So, once we have these cutting edge computing techniques powered by deep learning, powered by Gen AI, what opportunities do we have to revisit long-standing challenges in sustainability? And this is very broad. There are, you could probably break it down into even hundreds of different domains, and it's super exciting, super open. There's so much to do in this area. My personal work is at the intersection of AI and mobility. I will say my background is in electrical engineering and computer science. All of my degrees are in EECS, but I've really been drawn to applications. Even while I was studying, I knew I wanted to apply these techniques to some, societally relevant domain. And for those of you who are thinking along those lines, I highly encourage it. It's a super exciting journey. So I'll share a bit more of sort of the domain perspective. My personal research considers questions like, with these newfangled AI techniques and tools, and also what's emerging and, to what extent can we contribute to some of those? How can we superpower how we design future infrastructure systems? These are big, complex systems. They're hard to model. They're human decisions in the loop. There's so many interacting components, and they're really stretching the tools that we have today. If we don't have a new generation of tools, I think what's on the table or what's at stake is that we continue to build infrastructure systems that are more or less incremental, like deviations from prior systems, because those are the ones that we can sort of analyze, and these are expensive decisions. You want to build them, and you want to build them correctly. So it's right now safer to build a system that's like the one that we had before, rather than a riskier one that we don't have the sort of test of time. And so the extent to which AI can help us superpower our engineering tools to be much more accurate, to quantify uncertainty, to give us more options, to include, human in the loop interaction, to iterate on these designs, expose design options and whatnot. That's the kind of question that I'm interested in. So where I see myself in this community at the intersection of AI and mobility is sort of as a bridge. So to what extent can I help supply a new generation of tools powered by AI? So now let me tell you a bit about mobility and its relevance from the sustainability standpoint. I think of sustainability fairly broadly. So if you think about sustainable cities, it's not only about, say, greenhouse gas emissions, although transportation is the largest contributing sector of greenhouse gas emissions in the US, so it is one to take seriously. But it's also the leading cause of death among young people in the US, and, a billion people, maybe not a billion, a million people, sorry, are victims of traffic fatalities around the world, which is hugely tragic. These are folks who have so much more, potential, so many more years to be lived. Something like over half of the population does not have adequate access to mobility. Too young, too old, disabled, insufficient income. Access to a car is a major source of financial insecurity in this country. I also want to include financial sustainability. A huge issue in transportation is how do we maintain our infrastructure? How do we run our infrastructure at cost? So we hear so many debates about our crumbling roadways, our insufficient transit systems, and it's still, an open question to some extent. How do we, build these and maintain these in a sustainable manner? So those are some of the long-standing challenges, and we're not going to solve these in one day, but I invite you to join, because these are big problems. And the hope that we have in mobility is what's often called the 3 revolutions in mobility. These are technology driven. So autonomy, connectivity, there are actually 4, so I don't know why it's called 3. Autonomy, connectivity, sharing, and electrification. So popular concepts, technology enabled, and these are, we've already seen many of these revolutionize or start to revolutionize the transportation space. There's so much more to be done, and these introduce new complexities to our already complex systems, which further motivates advances in tools that can allow us to build the systems that we want to see, rather than systems that we happen to get because of some entrepreneur making a product. So there can be more intentional design, which is important at the infrastructure level. Also for those of you who don't think about mobility day in and day out like I do, mobility often breaks down into movement of people and then movement of goods. So here we're inclusive of systems like traffic systems, transit systems, but also logistics systems, supply chain, warehousing, and so on. So all of this together, there's an overwhelming complexity. Every intersection is different. People behave differently from one time of day to another, a different jurisdiction, different weather conditions. There's so much complexity, and so there's a lot of opportunity for AI to help in this space. So what I and my group focus on a bit more is on, it turns out when you model these problems, we also end up solving optimization problems like routing problems, these resource allocation problems, traffic control problems, and these boil down into some very hard control and optimization problems. So what I focus on is actually leveraging AI techniques to accelerate solving control and optimization problems. If you're thinking of reinforcement learning, that's one of the techniques and tools that we use. And it's like, a partial solution. So we are also innovating on some of the fundamentals when it comes to reinforcement learning, as well as looking at more practical alternatives, which I'm also happy to share. So we look at a lot of these optimization problems turn out to be combinatorial in nature, so combinatorial optimization problems. And we have a line of work, which I'm very excited about, that uses learning to leverage existing solvers that work very well and further accelerate those. So this is a line of work that we call learning guided optimization that's achieving the best of both worlds. Oftentimes with the DeepRL approach, we're trying to replace the solver entirely. Here we're trying to combine. So we work on both replacing when we don't have, already a good solver, we want to just do better, or if we already have a good solver, then can we make our solvers more flexible so that we can stretch their power to support some of these modeling, control, and optimization problems. I think I'll turn it back to our host here, and maybe I'll just close by saying that the topics here are all very interdisciplinary, and I think there's a lot that we can discuss and comment on in that direction.
Thank you, Kathy. All right, well, thank you for all those wonderful introductions. And, having a background in transportation systems engineering myself, I loved hearing that you're working on some, developing new tools in the mobility space. I'd love to see how they get applied in real life sometime soon. So we spent quite a bit of time talking about the challenges and the opportunities in the space. So I'd like to sort of make a pivot and talk about how we can solve them. So to start, what are some of the most exciting innovations or breakthroughs in the space that you see right now?
It's very hard to name innovation, but I'll just share my experience a bit. I've been working on data center infrastructure and the systems for 15, 20 years. So when I started my career as a PhD student doing research, what we care a lot is about performance, right? If we can make, say, MapReduce jobs and today machine learning system a bit faster, serving more requests, we're excited. And when I work with the superscalers like Google, Meta, Amazon, Microsoft, I guess a lot of you work with as well. They're excited too, because high performance means better customers, revenues, more satisfying customers. But only in recent few years, I start to hear the word energy a lot. It's mainly driven by machine learning applications. I would say the biggest innovation what we all seeing today is these models are getting super big, and they are so attractive that so many users want to use them. So the scale of it in terms of serving is also really big. And to the level where the energy supply to one data center site start to be so limited. We're hitting the energy war in scaling. So no matter how much we innovate our software systems, the energy is just not enough there. So I think people have started to take first steps in addressing these problems. So in the software system layer where I'm interested in, people have been innovating energy aware or carbon aware job scheduling solutions to just squeeze in the software and hardware layer so that we can fit the energy constraint. But there are yet a lot more one can do. Now energy becomes a major goal rather than performance in terms of scaling these systems. So if we look at system lobs, there's apart from job scheduling, there's data placement issues. There's also the way you can fine-tune your system, adaptively change your systems as resource changes. There's ways you can map it to different heterogeneous hardware. You can even reconfigure this hardware quite differently, ranging from changing GPU frequency to different smart data structures and algorithms you can run on these devices. So there are a lot more innovations much needed to solve the grand challenges of the energy needs and more broadly the carbon issues we've seen.
Okay, so I think there's a couple of things that excite me, right? So one is that I feel like, we were doing work in sustainability for computing, these sorts of things. Frankly, I had started some of this work, even in 2010, and I remember even some work before that when we first started building data centers. So, it's been, I would say, on again, off again kind of a thing. We really need to focus on the energy, and then that's kind of expensive, and I really care about what they do, and we just plunge forward again. I feel like we're finally at a point where we really just can't do that anymore, right? I mean, if you look at it, some of the statistics are I think they're saying that data centers by 2026 be consuming the amount of energy of somewhere between, Japan and Russia. So like it's crazy. Gen AI supposedly by 2027, the energy consumption for that is supposed to be at the level of energy that Spain as a nation consumed in 2022, right? So the numbers are just mind-blowing. A single ChatGPT conversation supposedly consumes about, a bottle of water in terms of the water consumption. So like we're kind of now at this place where like, I just do not think we can look away anymore. It's just like, it's in our faces, it's right there, and it just keeps growing. Like these numbers that I'm telling you, 2026, 2027, these are like increases of like 70% a year. This is insane because we know what we're doing now, right? And then, if that's going to keep going. So I think that, while I do also realize that, it's still, I'm conflicted in that, while I feel like, okay, this is good, we can't turn away from this anymore, we really have to go. But then when you see the numbers, it's like, okay, well, we have reason to kind of feel a little bit guilty about this, right? So I think it's something that we really have to go after. So that's one thing that I think is important and kind of exciting about it. I think in terms of, areas where, some exciting things are happening in this space, I think we are starting and people are becoming more cognizant of a couple of things about the model. So one is that, I mentioned this earlier, you don't always need the biggest models. Sometimes we can do things with smaller models. Now, there's a balance there, right? If we were taking these smaller models and then we're having to refine tune them for every task that we go after, it's not solving the problem, right? But the smaller models are becoming more usable for more tasks. So I think that's probably a good trend. I think the other thing is that, people often, sometimes people maybe that are not in the field think of, these AI services as a model. In many cases, they're not really a model. Instead, they are a system or a workflow of models. So, and preferably, and in some cases, that's another role for the smaller models, is think about how do we do this as a system. I think that's kind of cool and exciting for us in the computer science space, because then we can look at it not just in terms of the cost of training and the cost of inference. We can also, because if I go back a few years, right, to early in my career, it was about designing, these computing systems. So we were designing operating systems, and we were designing network protocols to be efficient, and we were designing memory systems, and so on. And now generative AI is not just a model, right? It's a system of models, right? And a system of, better memory management and, orchestration, which was the old, equivalent of the operating system. And, how they communicate across. So like Pydantic AI, is a form of better enabling the communication across these different ones. So I think this is a nice and exciting area, is to think of these Gen AI systems not just as a single model that in some cases are even like opaque in terms of why do they work? How do they work so well? What's going on? But to think of it more as a system, I think that will be disruptive, because the other thing that happens is if it is a system, then we have more that we can manage, right? We can look at how it's consuming resources, how will we change within that. So there's more ability to introspect and to change, right? And then I think that also what happens is that then we can think about more tasks that we can solve with those systems of AI. So I think that trying to do more on the size of the models can probably be something that's very interesting. Another area that I'm pretty excited about, because we know we're not going to solve this with just more software, right? Even though that's my space, right? We have to also think about the hardware system. So there's nice areas in terms of hardware, software, co-design, right? So that we're looking better at, okay, what do these AI systems really need? And can we design the hardware such that it's a better fit for that? So one of the areas that's interesting in that space is what's referred to as analog computing systems, or analog AI, or AI chips. This is basically what they're doing is they're sending electrical pulse through a certain material, and that material has more or less resistance depending on the pulse that's being sent through. And because it's no longer binary, on off, but instead increasing and decreasing resistance, then you have a continuum of numbers, and you can think of that as kind of the synaptic weights that are part of the neural network. And so you've got like almost a a well-mirrored mapping from AI and neural networks onto the hardware, into hardware systems. And the analog systems, in terms of energy consumption, are vastly lower than today's systems. So IBM, created one of these first ones, analog chip, in 2021. It's still research, so it's not something that's for general deployment. I think right now they're at 17 million parameter models that they're able to get onto these chips, but it's an area, right? And I think that we need to have more of that measurement and understanding of what we're doing, and novel kind of interdisciplinary, co-design types of approaches that we might do for it. So I think those are some of the areas that I'm excited about.
Thank you. So from the application perspective, some of the promising breakthroughs, I'll try to give some that are sort of mobility specific, but then I'll try to tease some, well, they're still mobility specific from my standpoint, but maybe you can find similarities in other domains. So a couple of things that people are looking at in terms of sustainability is like material discovery. So in terms of electrification, we have electric vehicles, and these can, to some extent, be a one-to-one replacement for most small vehicles, but it's still a question when it comes to larger vehicles, so vans, medium-size and heavy-duty trucks. Also for larger vehicles like ships and aircraft. So there's a lot of interest in new battery compositions, as well as biofuels, novel biofuels that can be drop-in replacements for current fuels. And so these are still some of the open questions. And so the extent to which machine learning can help with materials discovery can be really important there. Another aspect, I mentioned safety as the grand moonshot when it comes to traffic systems. It's, like I said, the leading cause of death among young people, and it's so like preventable in some sense. And so a breakthrough, that is still being tested is like, highly accurate traffic models. These models that can really accurate reflect behavior of the road participants, trajectory prediction models. These are what are internally used by autonomous vehicles, and that's the primary source of deployment that we see right now. But there's a push from the US DOT to actually bring that technology into the infrastructure itself. So imagine that your stoplight could be watching for cases where if it, adjusted the traffic timing, adjusted the pedestrian sign, adjusted any aspect of the road infrastructure that can be actuated, could reduce the likelihood of a fatal crash. And those are sort of, you can think of this as other implementation pathways for hyper accurate behavior prediction models for traffic. And it's all Gen AI techniques that are currently used to develop these models. So I think that's something to keep an eye on, and I think there's a lot of opportunity in terms of different deployment pathways. One area that's close to my own heart that I think is always good to, as an entrepreneur, including as researchers, we're also to some extent entrepreneurs, is to look for small changes that you can make that make a big difference in the system. So some work that's close to my own heart is showing that a small fraction of vehicles, if deployed on roadways and controlled appropriately, so like automated vehicles, they have an outsized impact on traffic congestion. Okay, and traffic congestion is directly related to energy consumption, because all that excess, like stopping and going, is just burning gas or energy. And so looking for these leverage points, these small differences that can make a big difference, so that these can be more easily implemented. You don't need the whole system to adopt this technology. And so as an extension of this, I'll just give a shout out to Shreya Raghavan. Do you want to raise your hand? Wave. So Shreya is a student of mine, and she's working on some sort of extensions of this work. I think she has a poster this afternoon on controllable congestion, which is our concept, to try to make this practical at a larger scale, in a way that can interface directly with stakeholders at the state level, state DOT, municipal DOT level. So encourage you to stop by her poster. The last one I just want to mention is something that we usually don't think about in terms of an intervention for sustainability and mobility, because it's actually really cutely called immobility. And I think we're a little bit jaded from this because of COVID, but this would be like our metaverse, like stay at home, don't go outside, and we can save a lot of energy that way. That is still a solution on the table. We see that our technology is not there yet, right? Like we prefer, it is hugely beneficial to be interacting in person. I don't believe that that's like fundamentally always going to be the case, and there is room for AI to innovate in that direction as well.
Did you have something to add, Lisa?
Oh, no, sorry.
Okay, no worries.
Sharing this mic.
No worries. Okay, well, thank you so much for sharing those insights. Sounds like there's a lot of progress being made here. Just for the sake of time, I'm gonna move to one of our last questions. So as we look ahead, I'd love to hear your advice for those who are aspiring to make meaningful impact in each of your fields, our next generation of researchers or practitioners in the field. Let's change it around and let's go with Kathy first, actually, so you can give her the mic again.
Advice to our young researchers. I think it's really hard to make a difference. I used to be very bright-eyed and thought, okay, like you just like do something and then like it's a good idea and then the world adopts it and then you move on. It's so much harder. So I would just say that, this stuff is super important. And I think it's a huge privilege to actually be able to like try to make the world a better place. I would say you have to really keep in mind that it's a long-term mission, and you have to, it's a really hard work to do the right thing. But I will say that as you try to do the right thing, there are a lot of people who will identify, who can see that passion and will help you along the way. And I myself have been helped along the way by people who saw that, I was trying to move in the right direction. So just like keep your spirit high. It is very hard. Interdisciplinary research is very hard. It's very hard to make a difference. It's very hard to convince stakeholders. But you do not need to do it like, all by yourself. There are a lot of folks who will be rooting for you. So, yeah.
Okay, let's see. So a couple of things. One would be that I think, so maybe the first one that I might say is that right now AI is going at this breakneck speed, right? Like every day it's something new that's out there, right? And it's a real challenge to keep up with, what's the latest model, what's the latest paper, to really feel like you're on top of it. And that's difficult, right? So what I would say is, try not to let that kind of overwhelm you. Like, just kind of keep going, on your path, find your space, try to keep up with it, right? Keep up with the space, understand what's happening around you, but, keep pushing forward on that. The other thing that I would say is that find sustainability, efficiency, all of these things in whatever you're doing, right? In other words, it doesn't just have to be the big project that's going to save the world, right? Like there's a lot of things we can do every day, just make my code a little bit more efficient, just try to be smart in terms of which model I'm using for which task, like, try to, do the measurements and see which algorithm really is making a difference in terms of consumption or resource usage or these sorts of things. So like just kind of embody it in everything you're doing, so that it's not like you're just going after the home run of the of the sustainability projects. Those are important and we have to do those, but I think there's a lot that we could be doing just in our daily lives. And then I think in terms of the bigger projects, and when you're trying to go after them, a lot of times we have these ideas and it's like, okay, this is going to save the world, and I just have to get that message out there. In order to do that, you need other people to believe in it. You need people that are going to work with you on it. You're going to need managers or executives to invest in it, so that you have a bigger team, or you're going to need VC to invest in it, or whatever the case may be. And so I would say, keep at it in terms of what's the return on investment, what's the impact that this would actually have, with objectively, quantifiable, the numbers of it, and then when you bring those numbers to someone to try to get that additional, investment, buy-in, collaboration, there may well be some pushback, but that's okay, right? They're telling you another dimension to look at, and then you go back and you try to look at that dimension as well, and then you keep getting stronger and better in terms of how you do that, because in the end, that's what they're looking for. It's not that, sometimes at least, it feels like, at least for me when I was early in my career, I have this idea and it's going to change the world and it's great, and I go and present it and it's like, well, I don't know, right? And I couldn't always understand that, but I think if you stay in the numbers and keep trying to adapt and refine those numbers, then that can make a big difference. It gives you some grounding, something to have a conversation on.
So I have two tips. One is more technical perspective, another is more career perspective. So for technical perspective, I think for us who work on sustainability, it's an interdisciplinary area. It's really important to join efforts from different aspects. Just from system perspective, I have been talking to innovators who say, oh, I have a really fast, energy efficient optical network links. Could I change the world by making data centers more sustainable? I think this is a great technique, but we need to combine it with great hardware, right? We need to combine it with a software solution that can leverage this high speed. We need to build end-to-end machine learning system that could maybe generate data that can feed into the link, and maybe in the end, take the data from the link and drive the model, right? It depends on what kind of model can run it better on it. And finally, what kind of application can run on this, can use these models, right? So it's really the end-to-end ecosystem. So if you're looking for especially for students and researchers who focus on specific area where you have strengths, trying to bridge out and think about the end-to-end impact of your work. And that also means that team up with people in other aspects, so that make sure the specific innovation you have in your specific area can have the end-to-end like sustainability gains, energy gains, and performance gains. And then that leads to the career kind of suggestion, like it's very hard today to make big impact with single person teams. It's really important to team up, especially this interdisciplinary area. It's important to find partners who can work on other aspects, whether it's in different discipline experts or people who really understand the applications, who really understand the kind of resource constraint, so they can all work together to build an end-to-end system that can actually make big impact.
Great. Well, thank you so much for these words of wisdom. Yeah, I mean, moving forward, I will definitely be more mindful about my code and its sustainability. Before I ask ChatGPT to fix my code next time, I'll be thinking about the amount of energy and water it's using. Yeah, and I don't know how much time we have left, but I would like to turn it over to you, our audience. So please raise your hand if you have any questions, and we'll open the floor for discussion.
Hi, Maureen Mayer, and I have a question for Lisa. Because you were mentioning that you were going to try to create different database structures, like for tensors and natural language data and images. And have you thought of having any sort of database for models? Like, for instance, now that it's a system of systems sort of thing, workflow.
We do some of that. What I would say is that I would say there's kind of two things that are related to that I'm aware of. So one of them is just better cataloging of the models such that we can find them, and then cataloging in a way such that we can there's some algorithms in terms of being able to deploy multiple models and then being able to direct across those depending on, what might be a good fit. So the idea would be, can you kind of match not just like where it does well, but also, the energy efficiency and all of these sorts of, so there's that one piece of it. There's another piece that's completely separate, sort of an idea that we've been kicking around, but it's early idea is to say, maybe we should think of, instead of thinking of a database as just the traditional database, the model is a form of a database, right? It is retaining a lot of information from which we can query it and get answers. And so should we be rethinking of, the databases not just as, these different representations, but actually a model as a database. So I'm not sure if that relates to what you were asking or not, but yeah. Yeah, there's a lot of, so these are research ideas, no question about it. And I think one of the big problems that we really are facing is that we just keep bringing the data into many different representations, right? So we bring it into, the raw data, and then we bring it, like people who are building these systems that are like chat systems that are able to answer and so on. Many times they're having to create, summaries, and then summaries of the summaries, and then summaries of the summaries of the summaries, and we're persisting all of this information so that we can have good response time, and it's, so I do really think that, and this is something, like I said, that we're working on, I do actually really think that this data management, data representation space is really quite ripe for doing some major, changes to it. But I would say right now, if there's not something that's like a clear leader in terms of which of these ideas, there's a lot of experimentation that's happening in this. Okay, thank you.
I have a question for Kathy. I was wondering, sorry, Mo Craft from IBM. I just have a very simple question, hopefully, but I was wondering if there's any innovation in public transportation.
We're working on some, but TBD on whether it works out because it's research. So what I will say is that there are innovations in public transit. Some of the more active areas that have already are a bit further along and have started rolling out have to do with paratransit and microtransit. So like mini buses. And so supplementing the fixed line bus routes with, or like rail with smaller, more flexible transit. And these are often contracted by the local transit agencies. And you can think of this as like your Uber, but potentially lower cost because they can pick up a number of people along the way. These also offer advanced scheduling, so often you can request a ride like a day in advance. So many of these systems are actually operational, and there are opportunities for machine learning to help with the optimization of these problems. Especially these problems can be very large, because if you're optimizing over a whole day of requests, this is very different from the Uber, Lyft style request, which takes a batch of requests over 30 seconds and runs these. And so the number of requests in a local geographic area is quite small. So there are open challenges there. That is a very active area of research. Yeah. I guess another one that I'll mention is there's a lot of interest right now in how well we can model how well we can model like how expensive rail projects will be, and that's also something that potentially machine learning can help with.
Hello, can you hear me?
Yes.
Also a question for Kathy. So I took a look at the poster and I was wondering how you got to, I know there was like unpreventable congestion and then the preventable congestion. So how did you arrive, or how did you figure out what was preventable congestion? Yeah.
Yeah, great question. And I encourage you to have a follow-up discussion with Shreya. But just for everybody, so we're designing this alternative measure for congestion. It's called controllable congestion, and I think that this generalizes potentially to other fields, other domains of sustainability. The key idea is that like. So in traffic systems, it appears that we settled on a metric for congestion that was easy to compute, but actually, like we make decisions based on these metrics, and they can have unintended consequences. So our traditional measure of congestion is delay. So this is a really good measure for computational purposes. It's very easy to compute. You take someone's travel time, you subtract it by the travel time that they would experience if there was no one else on the road. Okay, so free flow travel time. And then you try to minimize this quantity. What you get naturally by optimizing this metric is that you want to build more roads, right? You want more lanes. You want to basically increase the capacity of your system. So we decided, some of this congestion some of this delay is going to be lower cost to manage, and some of it's going to be higher cost to manage. If you have to build another lane, it's hugely expensive. If you can manage it by any means, then let's call that our notion of controllable congestion. So hopefully that answers your question. It is controllable by any means, fixing supply and demand. Okay, whereas the general notion of congestion would say, okay, we can actually also alter supply. We can, expand the roadways to mitigate congestion. So here, that's why we call it controllable. And so the general lesson is this new measure, I guess I didn't say, is hard to optimize. You have to solve an optimal control problem over a long horizon. You need accurate traffic models. This is potentially can be enabled through advances in AI. And so potentially there are other opportunities across other domains where we've settled on some metrics that are easy proxies, but maybe now we can do better.
Hi, my name is Claire. I work at IBM, and I'm working on a rail project in Norway. And I'm just wondering, how far off are we from having rail between major cities? The only rail that I've ever used is between Boston and New York, and those tickets are super expensive. Yeah, and I know it's a really complex question, but I'm just curious. I'd love to work here.
I guess you mean rail in the US.
Yes.
This is not my area of expertise.
It was a far shot, yeah.
I am starting to engage in some conversations for whom this is their area of expertise, and we are hoping to supply some AI expertise to help with, as I mentioned earlier, the cost part of this aspect, this broader picture. So I honestly have no idea, but what I hope that AI can help with is improving on the accurate assessment of return on investment. Right now, there's a bit of what we suspect to be gaming of the system. Like you're incentivized to project higher ridership to justify a larger investment from the federal government. This is true for road infrastructure, is true for rail infrastructure. I currently am not sure the extent of the problem, but this is something that lower cost auditing through machine learning could potentially help to address. And so, then indirectly, hopefully this can contribute to, making rail a reality in this country.
Thank you.
Thank you. My name is Hong. I'm from Vanguard. I traveled from Pennsylvania to here. My question is actually for Professor Ming Nan. I think what you talked about is how to reducing the cost, or the compute cost and carbon generation in the in the data center. And I recall this morning, Professor Van from MIT, right, also talked about similar topic. But where her focus area is how reduce the data movement, etc. And then you are talking about the materials and then how we actually can make sure those hardwares can be reused. You also brought up a good point where, like, I think the researchers should come together. It's a teamwork, solve the problem together. Just curious, is there any collaboration between Harvard and MIT on this particular topic?
So I myself are involved in multiple big projects in this area. The first one is the Carbon Connect. Unfortunately, MIT is not in it, but it does group together researchers from Harvard, UPenn, CMU, Caltech, a bunch of institutes together, because there are people who are experts on the material side. There are people who are like me on the more system side. There are also people who are on the economic side, policy side. So we are sitting together to see how to reduce carbon emission in data centers and solve the whole ecosystem problem. And another big effort I was just trying to start with, and hopefully this time we can involve MIT, is the Power and AI initiative. We're starting at Harvard. The goal is to, again, from the energy perspective, getting grid operators and the data center operators together so that we can jointly solve the grand challenge we're facing, the big pressure we get from the involvement of ML systems.
All right, I think that's all the time we have. Well, thank you all for your thoughtful questions. And as we wrap up, I'd love to extend a huge thank you to our amazing panelists today. So let's give them a big round of applause.